Hello and welcome to our presentation. My name is Sajivan Odhikari and I am going to present our paper Accelerating Text Communication via Abbreviated Sentence Input. When users with motor impairments enter text using a virtual keyboard, their input may be slow and inaccurate. For example, people with ALS may need to type characters by pointing at them with a head or eye tracker and dwelling for a fixed amount of time. In such situations, the rate at which a user can input text is limited. Word completions can accelerate a user's text entry rate by predicting the most probable next word. However, monitoring word predictions carries a cognitive cost and it takes effort to select a word completion even once it is perceived. As an alternative to word completion, in this work we propose entering text using sentence abbreviation. In particular, we explore allowing users to optionally skip entering spaces and mid-word vowels. We make the following contributions. First, we modify a probabilistic recognizer to decode abbreviated sentence input by inserting omitted mid-word vowels and spaces. Second, we show how to improve language model performance for conversational style text by selecting well-matched training data and using a neural model based on BERT. Third, we compared the impact of using a neural language model in our decoder search versus a typical n-gram language model. Finally, we validate our findings in a user study where users write text in a simulated rate-limited input setting. We decided to support this style of abbreviated input based on past work and the free-form abbreviation study we conducted on Amazon Mechanical Turk. In this study, 200 workers abbreviated short email messages. Here you can see the instructions we gave the workers. We instructed workers to shorten words by removing or changing letters, but not to omit words entirely and not to rephrase or summarize the original message. In this study, we found on an average 21% of a word's letters were deleted. Of this, 16% were consonants and 42% were vowels. If we consider the letter position in words, 90% of middle letters were deleted. This confirmed our initial belief that people delete vowels more frequently and usually retain the first letter of words. We took workers' abbreviated text and fed them into a decoder to expand. The decoder used beam search guided by a language model to explore inserting all possible characters at all possible positions of the abbreviated input. Each dot on this graph is a single sentence. The x-axis is the percentage of letters omitted in a sentence and the y-axis is the character error rate of the automatically expanded sentence. We found that for sentences where 30% or less of characters are omitted, the expanded sentence had a character error rate below 5%. This seemed promising given the simple model we used in this experiment. We think abbreviated input may most benefit users with slow input. From this point on, we focus on optimizing our system for use by augmentative and alternative communication or AAC users. AAC users may not be able to speak due to a condition such as ALS. Sentence abbreviation may be particularly useful for short phrases with predictable language. Our search-based approach relies heavily on a language model to infer the most likely expanded sentence. So next we explored how to optimize our language model for everyday conversational style phrases. We used a crowdsourced conversational dataset as our target in-domain text. You can see some examples here showing the difference between sentences typical of the in-domain and out-of-domain sets. Using the crowdsourced dataset as our target domain, we selected sentences from 1 billion words of web text until we reached 100 million characters of training data. We selected sentences in three ways. First, as a baseline, we randomly selected sentences. Second, we calculated the cross-entropy difference of a sentence using models trained on subsets of the in-domain and out-of-domain data and took the highest scoring sentences. Third, we trained a BERT-based binary classifier on examples of in-domain and out-of-domain sentences. We then used this classifier to find the probability of sentences being in-domain in our web text. We took the sentences with the highest probability. Some example text of the selected sentences are shown here. We trained a 12-gram character language model on the 3 sets of selected data. The average number of words in a sentence in the cross entropy and bird selected datasets were less than 14. We also calculated the perplexity of the model on 2 conversational test sets. Results show that the models trained with the cross entropy difference and bird selected data had similar perplexity, and both were lower than the perplexity of the model trained on randomly selected data. To expand abbreviated input, we use the velocitap decoder. Velocitap takes a series of 2D tab locations and searches for the most probable text using an n-gram language model. It can insert characters without consuming a tab by incurring an insertion penalty. It can also delete a tab by incurring a deletion penalty. We modified velocitap to insert mid-word vowels by adding a vowel insertion penalty. We also extended velocitap to use a recurrent neural network language model. The neural model worked in 2 ways, either as an alternative to the n-gram language model or to rescore the n-based hypothesis list generated by an n-gram based search. We used a recurrent neural network language model trained on bird selected data in these experiments. We tested the modified decoder to expand noisy abbreviated touchscreen keyboard input from hundreds of users. We created a development set and a test set from touchscreen tab data from hundreds of users collected in previous studies on touchscreen phones and watches. We concatenated all the tabs to create single sentence sequences without spaces. Then we played back tabs to the decoder, dropping mid-word vowels with a probability of either 0.5 or 1.0. We tuned the hyperparameters of our decoder on the development set and tested its performance on the unseen test set. The table here shows the recognition results. We calculated character error rate or CER with 2 different mid-word vowel drop probabilities and 3 different decoder search methods. As you can see, using the n-gram model for search and rescoring with the recurrent neural network language model resulted in similar error rates to searching with the recurrent neural network language model, but was much faster. The error rate increased as more aggressive abbreviation was done by dropping all mid-word vowels. With a 0.5 drop probability, the character error rates were around 4 to 5%, and with a 1.0 drop probability, the character error rates were 8 to 10%. The compression rate with a 0.5 drop probability was 28%, and with a 1.0 drop probability was 38%. Dropping half of vowels, the decoder recognized 72% sentences completely correct, while it recognized only 59% sentences completely correct if all mid-word vowels were dropped. To see if our system would provide practical user benefits, we conducted a user study with 2 counterbalanced conditions. Users were assigned the tasks to enter text on a smartphone web keyboard as quickly and accurately as possible. In one condition, users enter text using the traditional word at a time input with word predictions. In the second condition, users were instructed to enter a sentence without spaces and mid-word vowels. To simulate a slow input user, we had users dwell on a key for 1 second in order to click it. A circular progress bar around the task location was shown to indicate the dwell time. Users entered 24 phrases in each condition. Here in this video, you can see a user entering the phrase, "Are we finished yet?" using word at a time input. The keyboard has 3 prediction slots above it. Notice how the user is dwelling on a key to click it and how the user is selecting words from the word prediction slots. In this video, you can see a user entering the phrase, "I forgot about that" in the abbreviated sentence input condition. The prediction slots and the spacebar are missing from the keyboard. Notice how the user is skipping entering the mid-word vowels. Results show that with the word at a time input, users enter text at around 10 words per minute with an error rate of only 0.3%. On the other hand, with the abbreviated sentence input, users were significantly slower at 9 words per minute and also significantly less accurate with an error rate of 7.2%. However, the average performance of the users on the last 8 phrases was mostly similar in both conditions at 9.9 words per minute and 9.6 words per minute. This suggests that with practice, sentence abbreviation could achieve comparable speed. When users provided abbreviated input consisting of all the correct letters except mid-word vowels, 90% of these phrases were expanded correctly. To conclude, we investigated accelerating text communication for slow input users by sentence abbreviation. We found dropping mid-word vowels and the spaces can compress the amount of input significantly and has the potential to match the speed of word at a time input with autocompletions. Interestingly, in the last 8 phrases of a 30-minute typing session, novices typed with an entry rate of 9.6 words per minute in the abbreviated sentence condition compared to 9.9 words per minute in the word condition. We found if sentences were abbreviated by removing mid-word vowels and space between words, our recognizer expanded them correctly 90% of the time. At its current state, our work provides some directions to improve our system. We would also like to test our system with ASC users, but we believe our paper is a first step in producing a viable prototype for testing with users with actual input rate limitations.